For any exam-related queries, call us at +1 678 648 4277. You can mail us at info@livexamhelper.com or reach us at https://www.livexamhelper.com. 1. A long permanent magnet has a remnant induction of in the y direction. Its cross-section in the xy plane is square measuring AXA and its length is very large in the z direction. A. Sketch the H-vector fields near the top and bottom surfaces. 10. B. Calculate the y component of the field MOE at the midpoint just outside the top surface. Show your equations and get a numerical result. The numbers were chosen so a calculator would not be necessary. ANS 1A. Field emanates from +N poles and terminates on VS poles as sketched. livexamhelper.com. 2. Consider the data below. A. Explain why the magnetic moment per formula unit, Fu, increases when small amounts of ZNO are substituted for MNO in the ferrite MNO Fe2O3. B. Why does the moment per Fu then start decreasing when the Zn concentration exceeds about 50%? C. Speculate about why the peak in moment per Fu occurs in NiZn ferrite at a smaller Zn concentration than it does in MnZn ferrite. livexamhelper.com. ANS 2A. There are two cation sites in the spinel structure, tetrahedral A and octahedral B. One cation per Fu occupies an A site and two occupy B sites. The different transition metal ions prefer these sites as indicated in the figure. The moments on the ions of interest are Fe2 plus equals 4, Fe3 plus equals 5, Mn2 plus equals 5, Zn2 plus equals 0, and Ni2 plus equals 2 Bohr magnetons. The exchange interactions are of the antiferromagnetic AF superexchange type, i.e. cation moments coupled through the p orbitals of an intervening anion, in this case, oxygen. The exchange interactions, in order of decreasing strength, are AB, BB, AA no interaction. In MNO Fe2O3, ABMN2 plus 2FE3. -5 plus 10 net moment is +5. Introduction of Zn2 plus displaces Mn2 equals from a site to B site, increasing the net moment. B. At some Zn concentration, the ABAF exchange interaction, proportional to becomes weaker than the BBAF exchange interaction because of the smallness of SA. At that point, the B site moment decreases and the net moment begins to decrease. livexamhelper.com. C. In Ni ferrite, the Ni ion occupies the B site with one of the Fe3 plus ions. The other Fe3 plus is on the A site. The AB exchange interaction energy is weaker than that in Mn ferrite because of the smaller Ni moment. Thus, it gives way to the antiferromagnetic AA interaction at a lower Zn concentration. 3. You make some HCP cobalt and some HCP cobalt-rich magnetic alloys. You measure their anisotropy constants to be as follows. Q1 is equal to 4.1 times 105J/M3, Ku2 is equal to 1.5 times 105J/M3. Co-rich alloy A, Q1 equals -5.0x 105J/M3, Q2 equals plus 5x 105J/M3. U data were analyzed using the form Fa equals K0 plus Q1 sin 2Q plus Q2 sin 4Q plus. A. What is the stable direction, in H equals 0, of magnetization in the Co? B. What is the stable direction, in H equals 0, of magnetization in co-rich alloy A? Show your work. C. In alloy A, you measure L0001 equals plus 100x 10 to 6. Give an expression and a numerical result for the stress along the C-axis that is just sufficient to bring M into the base plane. Q equals 90 O. Identify the stress as tensile or compressive. Use 3/2 ls form not BA. ANS 3A M is stable at for Co from the minima in F. B for alloy A, see sketch below, right. liveexamhelper.com. B, in the case of alloy A, cosc plus 4Q 2 cosc 3Q. You can divide by cosc because it is obvious from the figure that it is not zero near the energy minimum. Thus, sin 2Q equals Q1/2Q2 is equal to 0.5, Q equals 45 O. C. Putting Q equals 45 O into Fa gives for the depth of the energy well in alloy AFA, 45, F0, equals minus 1.25 x 105 J/M3. Given the positive magnetostriction, it should be clear that a compressive stress along the C-axis will tend to stabilize M in the base plane. The stress energy stabilizing M at Q equals 90 O is 3/2 SL, which could be C equated to Fa, 45, Fa0. Thus, S equals minus 1.25 x 105/1.5 x 10 to 4. S is equal to 0.83 times 109 nm2 equals 0.83 GPa. More accurately, we should minimize the anisotropy plus magnetoelastic energies and get the full solution. We express the angular dependence of the Me energy as 3/2 ls sin 2Q because a compressive stress stabilizes Q equals 90 O. Energy minimization gives liveexamhelper.com. Equating the square bracket term to 0 shows that the stress dependence of the in-plane component of magnetization, namely M equals sinc, has a zero stress value of 0.707 as we expect from its 45 O equilibrium orientation. Upon increasing the stress, sinc increases like the square root of S, reaching unity, saturation at 4. On your answer sheet, sketch, as a solid line, the block domain wall profile below which applies for a material with. Use your knowledge of the equilibrium torque balance at every point in a domain wall to sketch, as a dashed line, what happens to the domain wall profile if Q1 equals 0 and Q2 0. Explain in 1 or 2 sentences. liveexamhelper.com. B. Use order of magnitude estimates and scaling arguments to determine which defect would have a greater pinning effect on a domain wall in cobalt and Y. You'll need to calculate the domain wall width in Co. Use A equals 10 to 11 J/M and look up a constant in CH7I, an interstitial impurity that produces a strain field dropping from E equals 1% and extending for about 60 nanometers about its site, or in phase substitutional defect that has a magnetic moment 30% greater than that of the co-atomate. Replaced? 2. A region about 60 nanometers in diameter in which the stacking faults change the cobalt structure to FCC, and thereby reduces the magnetocrystalline anisotropy by an order of magnitude in that region, or the stress field above in I. liveexamhelper.com. ANS 4. A. The zero torque condition is the second-order anisotropy. Function. It is flatter, smaller slope, at small angles and steeper near 700 than is the first-order anisotropy function. Therefore, the curvature of the second-order function is greater between these limits. The shape of the second-order anisotropy block wall is suggested by the bold dots on part of the figure above. B. Wall width is I. Strain field produces a magnetoelastic defect of approximate strength B1E is equal to 6 times 106 x 0.01 J/M3 with a range of order 60 nanometers.